In order to understand what was going on with the inconsistent and dependent equations in two variables, we looked at the lines involved. In order to understand what's happening with inconsistent and dependent systems of three equations, we'll need to look at pictures of those equations as well. So we need to ask, what does the graph of an equation in three variables even look like? So remember when we established our x and y axis, we had one dimension for x and labeled a bunch of vertical lines, another dimension for y and labeled a bunch of horizontal lines, and then we plotted points that way. And the graph of an equation was a picture showing all of the solutions to that equation on that grid. When we have two variables, we need two axes. But if we have three variables, there are three values, and so we need three axes. And that's difficult because our piece of paper only has two dimensions. We're actually going to now try to draw some three-dimensional pictures, and that's difficult. When we draw a set of three axes, we draw the third axis on a diagonal. And depending on exactly what you're doing, sometimes you'll draw x and y where they normally are, and then z coming out of the screen at you, drawn on a diagonal, but imagine that it's coming out of the screen at you. Or sometimes we'll call this one x, this one y, and this one z. So we'll turn the whole system so that x and y are kind of in a flat horizontal plane, and then z is going upward. The reason for that is kind of complicated, and we won't go into it here. But keep in mind that you'll sometimes see the axes arranged in a different way than what I'm showing you in this picture. Okay, let's try to see what the graph of this equation we're talking about looks like. It's easy to see if we want x, y, and z to add up to 2. But one way to do that is to make one of them 2 and the other 2 0. So 2, 0, 0, that's the 2 on the x-axis. 0, 2, 0, that's the 2 on the y-axis. And 0, 0, 2, that's the 2 on the z-axis. And then, what else can we do? Well, we can keep x 0, and we can take all of the pairs of y and z that add up to 2. They're going to lie on the line connecting these 2 points. We could keep y 0 and take all the pairs x and z that add up to 2. They're going to lie on the line connecting these 2 points. And then we can keep z 0 and take all the pairs x and y that add up to 2. They're going to lie on the line connecting those 2 points. And I just connected the points. I'm only working with the part right now where x, y, and z are all positive, because that's going to be easier to draw. What we end up getting, as far as x, y, and z all positive, is this sort of little triangular surface stretched out between those 3 points. And then we can just extend that into negative values of x, y, and z. And what we end up with is a plane in space. Now, if we wanted to invest a bunch of effort into becoming very good 3D draftspeople, getting very good at three-dimensional drafting, we could now try to actually graph some equations in 3 variables and look at how their graphs actually look. But that would be a lot of work for relatively little payout, especially in the 21st century, where if you want something like that drafted in 3D, you have a computer do it. So I have some examples here where I've had the computer draft the picture for us. And we're going to use that to analyze this. And I've had the computer draft examples that look nice rather than examples that correspond to any specific equations. So, what does this actually look like? The normal system, the typical system, where we have a unique solution to a system of 3 equations and 3 variables, looks like this. In this image, we have 3 planes intersecting at a point. In 2 dimensions, the typical thing to have happen was 2 lines intersecting at a point. In space, the typical thing to have happen is 3 planes intersecting at a point. In the plane, there were only 2 things that could go wrong. Either we had 2 parallel lines, or we had 2 equations that actually described the same line. In space, because we have 3 planes to play around with, there are more things that can happen. And that's what we're going to discuss in the next 2 videos.